Hello, hello. We're going to be working with differentiating power functions. Now, you should at this point already know what the power rule for differentiating a power function is. And what we're going to do is just add a couple other fundamental rules that you need to know that are going to work for differentiating not only power functions, which we're going to focus on here, but any type of function truly. All right, so here's the goal. You're going to learn to apply the constant rule, the constant multiple rule, and the sum or difference rule to differentiate power functions. Now let's start with the constant rule. And the constant rule turns out to be one of the simplest rules you can possibly have for any kind of math thing, truly. All right, here's a constant rule for differentiating functions. If f of x is equal to c, where c is any real number, or in other words, if you have a function that's just equal to a constant, like 3 or -1/2 or something like that, then the derivative of that function f is going to be equal to 0 every time. Whenever you take the derivative of a constant, 0 is always what you get as a result. So for instance, suppose you had a function f of x equal to -7, then the derivative of f would be 0. If f of x equals pi, which is just a constant value, then f prime of x equals 0. Truly, it doesn't get any simpler than that. The derivative of any constant is 0. Okay, well, what about the constant multiple rule? These names sound very similar, but last time we were just talking about the function was equal to a constant. This time, we're talking about a situation where we have a function that's being multiplied by a constant. It says if y is equal to c times some function f of x, where c is any real number. Okay, so here's the function, here's the constant the function that's being multiplied by. Anytime you have a function being multiplied by a constant, then the derivative, y prime, is going to be equal to c times the derivative of that function. Okay, so essentially here's how this works. Let's suppose that a function f of x is equal to 15 times x to the 6th power. Well, we've learned how to use the power rule in order to differentiate x to the 6th power. And what the constant multiple rule tells us we could do is take the derivative of a power function that's being multiplied by a constant simply by doing this. We can say f prime of x is going to equal whatever that constant was, 15 in this case, times the derivative of the power function. Now, or any function, doesn't have to be a power function. So remember with the power rule, we're going to bring that exponent to the front. We're going to go ahead and decrease the exponent by 1. There you go. And then that means that f prime of x here is going to be 90 x to the 5th power. Okay, so constant multiple rule. If you have a function being multiplied by a constant, simply take the derivative of that function and then multiply by the constant that's already there. And then the last of the 3 rules that we were learning, something called the sum or difference rule. Now what the sum or difference rule is going to help us is in a situation where we've got a function that's made up of multiple terms, a power function in this case, but any function that's made up of multiple terms. If you have a function f of x that's equal to u of x plus or minus v of x. That might look complicated now, but it just means we've got 2 terms within our function. If that's the case, then simply f prime of x equals, not 0 as you might have just seen on the screen, but rather u prime of x plus or minus v prime of x. All right, in other words, if you've got more than one term in the function that you're trying to differentiate, then all you have to do is differentiate each term individually. Take the derivative of the first term, keep whatever addition sign or subtraction sign you have between the terms, and then differentiate the next term, and so forth. You can do that for as many terms as are in, well, a function that you're trying to differentiate. Let me give you an example there. Suppose we wanted to differentiate f of x is equal to x to the -2nd power minus x to the 5th plus 3. All right, simply all we've got to do to find the derivative of f prime of x, is we've got to differentiate each term in that polynomial function or power function. So we would have -2x to the -3rd minus 5x to the 4th And then I'm giving you a little practice with the constant rule here. The derivative, of course, of 3 is 0, so that term is going to go away. And then if you wanted to, you could rewrite this in simplest form, but the point was differentiate each term when differentiating a sum or a difference. And here you'll get negative 2 over x cubed minus 5x to the 4th power. Now let's go through and just do some differentiation where you're going to apply those rules along with the power rule. And let's start with this function that you see right here, f of x equals 4 over x cubed minus 5x squared. Now remember, the first thing that you're trying to do with the power rule is you're trying to rewrite every term, and well, now that we have more than one term, we're going to try to rewrite every term so that it's in the form ax to the nth power. Which for us here is going to mean that we're going to rewrite 4 over x cubed as 4x to the negative 3rd power. Now as soon as you've got that done, now we're ready to go ahead and take the derivative of the function. And let me go ahead and talk about the constant multiple rule in kind of another light. You know, if we just had x to the negative 3rd power, that you would bring the negative 3 to the front and make this exponent a negative 4. Well, if we're going to multiply this by 4 later on, we can go ahead and do it now. Whenever you have a coefficient for a power function, all you have to do is multiply it by the exponent of that power function when you differentiate. So we'll have negative 3 times 4. It's going to be negative 12x to the negative 4th power. And then minus, and we'll do the same thing here. To differentiate x squared, you would get 2x, wouldn't you? And then you multiply that by 5. So let's just do 2 times 5 now and get 10x. And then, as is always good practice, so let's rewrite this expression so it doesn't have any negative exponents. Make that negative 12 over x to the 4th minus 10x. Not too bad, right? Let's take a look at a couple more examples. All right, we got the function f of x equals 1/2 times the square of x plus 6. Now in a later video, I'll teach you a more direct way of doing this differentiation, but for right now, I'm only teaching you how to differentiate power functions because that's what we've learned. And so here's what I need to do. I need to rewrite this function so that it only has something in the form ax to the nth power. I need a bunch of terms that fit in this form right here basically. And in order to make that happen for this, I'm going to need to go ahead and square the x plus 6. So let's make this 1/2 times x squared plus 12x plus 36. And then we'll go ahead and distribute the 1/2. You got 1/2 x squared plus 6x plus 18. And now we've written the function so there's just one power term plus another power term plus another power term. We can go ahead and differentiate. All right, so for this first term, we'll bring the 2 out front and multiply it by 1/2. 2 times 1/2 is 1, right? And then we decrease the exponent. That'll give us just x to the 1st power for the first term. And then for the second term, we have an x to the 1st power right there. We'll bring that 1 out, multiply it by the 6. And then we make that x to the 0. And of course, x to the 0 power is really just 1. So that'll remain a constant. Then this constant term, of course, its derivative is going to be 0. So x plus 6 is the derivative for that function. All right, now for the last example. And we're going to treat this one very similarly to the previous example, by which I mean we would like to rewrite this function so that it's just a sum or difference of power terms that are in the form ax to the nth power. All right, now in order to do that, what we're going to need to do is distribute the square root of x. But before we even do that, let's go ahead and rewrite this, or each of these radical expressions, in exponential form instead. All right, so you know the square root of x would be x to the 1/2 power. Then the cube root of x is x to the 1/3 power, and the 6th root of x would be x to the 1/6 power. All right, now let's go ahead and use the distributive property. Now we're multiplying powers at the same base here, so you remember you add the exponents. Now when we get to adding the 1/2 plus the 1/3, the common denominator there is going to be 6, isn't it? So we can say this is 3/6 plus 2/6, so 5/6. All right, then keep the subtraction sign. And then we'll multiply x to the 1/2 times x to the 1/6 power. So we'll get x, and then the exponent for that product will be 1/2 plus 1/6, or 3/6 plus 1/6, which is 4/6, or 2/3. So there's our function. Now to find the derivative of that function. All right, well, simply use a power rule with each of these terms. We're going to bring the 5/6 out front, and then we'll copy down the x, and we need to decrease this exponent by 1. Now 5/6 minus 1 is negative 1/6. Then copy down the subtraction sign between the terms, bring the 2/3 out front, and then decrease the exponent by 1. 2/3 minus 1 is negative 1/3. And at that point, we're finished with the differentiation. It's just making this look a little nicer. And I'm going to rewrite this without any negative exponents. Now, keep in mind that the constants here are not being raised to these exponents. 5/6 is not being raised to the negative 1/6 power. Only the x is being raised to the negative 1/6 power. And in the second term, only the x is being raised to the negative 1/3 power. So, when you use the rules for negative exponents, that means you're just going to bring the x to the denominator, so you get 5 over 6x to the positive 1/6 power. And then minus 2, and we're bringing this x to the denominator as well, so over 3x to the positive 1/3 power. And the last thing I'm going to do is I'm going to replace the fractional exponents with radicals. Not because I have to, but just to show you what you're able to do. It makes it look neater a little bit. And again, keep in mind that the coefficient is not being raised to this exponent. It's only the x that's been raised. So we'll have 6 times the 6th root of x there, minus 2 over 3 times the cube root of of x. All right, so now you know how to differentiate constants. You know how to differentiate a function that's being multiplied by a constant. And you know how to differentiate a function that has multiple terms, all using the power rule along with the new rules that we just learned. Thanks for your attention, guys. See you next time.